What is infinity? Is it in our minds, or is it something real and tangible? Is it a matter for mathematics, or one for theology or cosmology? Is infinity something we can even measure? Poet William Blake, who lived at the turn of the 19th century, wrote, "To see a world in a grain of sand and a heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour." The mystery of infinity has intrigued mathematicians for thousands of years. Still, many of the greatest thinkers, from Pythagoras to Galileo, even the great Gauss, refused to tackle it, deeming infinity to be unthinkable. But believe it or not, the idea of infinity begins with something as simple as counting and the way in which we measure the world. As humans, we find hints of infinity as soon as we learn to count. Once we run out of fingers, we realize there might be a never-ending number of things, from the grains of sand on planet Earth to the stars in the heavens. Faced with orders of magnitude beyond what our human senses can comprehend, many great minds have concluded that infinity is outside the purview of mathematics and best left to philosophers and theologians. In fact, the subject has been taboo for mathematicians throughout much of history, perhaps most especially the ancient Greeks, because it seemed to pose a problem that could not be solved. Zeno of Elea, who predated Aristotle, wrote a series of paradoxes that still give us pause today. One of the best known tells the story of Achilles and the tortoise and their race. Achilles is such a fast runner, he gives the tortoise a head start. They each run at constant speeds. Achilles very fast, the tortoise very slow. After a finite amount of time, Achilles gets to where the tortoise started, but the tortoise will have moved on. It takes Achilles a finite amount of time to get to the tortoise's next spot, but by the time he arrives, the tortoise will have moved on from there as well, and so on, over and over again ad infinitum. Despite what our senses tell us, Zeno is telling us that Achilles will never catch the tortoise. Zeno's paradoxes were a big problem for the Greek philosophers, and they did just about everything they could to avoid confronting the infinite, because they based their arithmetic and their entire worldview on something much more tangible: geometry. Their notion of the mathematical and the physical was intimately linked to the practice of measuring objects using arbitrary but finite units, like the length of a finger or the width of a palm. And as we do today, units like inches or centimeters, these are arbitrary but commonly held divisions of length. Now, the Greeks believed that given any two lengths, an arbitrary unit of some kind could always be found to measure both lengths in whole number multiples, meaning that the two lengths are always commensurate or commensurable. Now, Pythagoras was perhaps the first to articulate this belief based on whole numbers, and it came from his observations about music. Pythagoras noted that if two commensurate strings were strummed to vibrate, then the tones that they produced would be pleasing in harmony. Thus, Pythagoras and his followers believed that all that is good and harmonious in the world must be based on whole number ratios, and that all measurement must be rational. It was a philosophy that became almost religious in nature. But then they encountered something that they couldn't explain with this rational model, something which challenged the very core of their beliefs: the diagonal of a square. Now, how could it be that a simple diagonal line could turn the Pythagoreans' world upside down? Because the fact is that the diagonal of the square is not commensurable with its side. Here's how first the Greek Hippasus and then his contemporary Theodorus of Cyrene reached this conclusion. Take a square whose side has length 1. Draw its diagonal, and we see that the square is now comprised of two triangles. Now use that diagonal as the side of a second square, and we see that the new, larger square is in fact made up of twice the number of triangles as the first, which means that it has twice the area. So the length of a diagonal of a 1-unit square is equal to the length of the side of a square that has twice the size. Hence, the diagonal's length is called the square root of 2. So far, so good, at least for the Greeks. After all, the diagonal is tangible. It's real, we can draw it, it's right there in a 1-unit square. But when Theodorus tried to measure the diagonal, he in essence discovered a paradox. Theodorus began by measuring one triangle, 1/2 of the square. Now remember, the Pythagoreans believed that units of measurement could be arbitrary, like the palm of a hand, or for us today, the length of an inch or a centimeter. But they also believe that there must be a common length that fits a whole number of times in both the length of the side and the diagonal. The measurements must be commensurate. When Theodorus tried this with, say, 4 units along each side of the square, he found that he couldn't measure the diagonal with a whole number of those units. There would be a small portion of a unit left remaining. In fact, no matter how many units we divide up each side of the square into, when we try to measure the diagonal with this basic unit, there's always some small amount left over. Now, this is a pretty interesting observation, but Theodorus went a big step further. He also developed a purely logical and ironclad proof that no such common unit can possibly exist. At the heart of this is something of the mystery of the infinite. Implicit in what Theodorus was tackling was the fact that in any measuring system that gave a whole number of units to the side, the diagonal would have a length that has to be expressed as an infinite decimal expansion. This is part of what it means to say that the square root of 2 is irrational. So, rather than be perturbed by the infinite, as for the Achilles and the tortoise paradox, Theodorus in some sense embraced the infinite. As individual humans, we might try fitting in a common unit many times in our lifetimes, but that number of attempts will only be finite. With his logical argument, Theodorus showed that even if an infinite number of humans each tried an infinite number of times to find a common unit of measure for the side length and the diagonal of a square, none will ever be found. Infinity. Theodorus contradicted the most basic of Pythagorean assumptions. There is no common length that measures both the side and the diagonal of a square. The two lengths are not commensurate. This in turn proves that the square root of 2, the numerical value of the diagonal of the square, is different. Its measurement lies somewhere between rational numbers. In modern language, its length is said to be irrational. With this discovery, the Pythagoreans' world was turned on its head. Numbers that had been previously unimaginable were now known and shown to exist. The square root of 2 being irrational means that it has a decimal expansion which continues forever without any repetition. So even using arbitrary units of measure, the Greeks discovered that they could not avoid the infinite. The square root of 2 and later pi were both represented by non-repeating infinite decimal expansions. Even so, many great thinkers who followed the Pythagoreans would continue to avoid infinity. Aristotle flatly refused to believe in what he called the actual infinite. In fact, he wrote, "Since no sensible magnitude is infinite, it is impossible to exceed every assigned magnitude. For if it were possible, there would be something bigger than the heavens." And in the 16th century, the great astronomer Galileo, he noticed that there seemed to be just as many square numbers as natural numbers. Though Galileo went no further with this idea, he wrote, "Infinity should obey a different arithmetic than finite numbers." But there were signs, or at least symbols, of change in the air. In 1665, noticing that his contemporaries were sneaking ideas of actual infinity into their work, English mathematician John Wallis first introduced the love knot, or lazy 8, as a symbol for infinity. Some authorities speculate that the symbol has its origins in the ancient Ouroboros, used to symbolize eternity. But wherever Wallis's infinity symbol came from, it took an ambitious young Russian-born mathematician named Georg Cantor to force the concept of infinity into mathematics once and for all. Cantor's first work was in the subject of number theory, the area of mathematics that seeks to reveal truths about the natural numbers. He revealed a previously unimagined beauty and richness, as well as paradox. With this, he discovered a whole new world of mathematics. So now we'll be speaking with Dr. Jim Tanton, the founding director of the St. Mark's Institute of Mathematics. Hi, Jim.
Hi.
Well, let's talk about infinity, a big subject, isn't it?
It is a big subject indeed, absolutely.
All right, so Cantor was really the first one to sort of take it on, right? Mano a mano, try to figure it out.
Absolutely, grab it by the horns and understand what's going on here. But the interesting thing is he didn't start right away with that concept. He went to a more fundamental question. What is a number? For example, here are some cats and some dogs.
Okay.
If I'm trying to define number in the first time and say, are these two sets, the set of cats, set of dogs, the same? I don't want to count them. I don't want to say the word 5.
Right.
But somehow I want to somehow demonstrate that these two sets are the same, equinumerous, or have the same cardinality.
Right.
How did Cantor do that without saying 5? Well, his idea is actually very simple. Here's my left hand.
Right.
Some number of digits. My right hand.
Right.
Some number of digits. How do I know these are the same? Just
Match
do
them
that.
up. Right.
Yep. Each digit on the left hand is matched with one digit on the right hand, and vice versa.
So one-to-one correspondence.
One-to-one correspondence. Yep. This hand right here represents 5.
Right, as does that set of cats.
Because my cats can match my digits. Those dogs can match my digits.
Right.
We have 5-ness under control now.
Right.
And the same thing, I'm going to do 902-ness or 3-ness, so forth.
Right. So every number will correspond to any set that somehow has a particular collection of things. So number turns into this abstract thing.
Set theory is becoming the fundamental concept of mathematics, not number itself. We use set theory to define a number.
Right, and then you can do a lot of arithmetic with set theory as well.
Absolutely,
fact, the
absolutely.
Whole way.
So this is the story I like best. It illustrates something that mathematicians love to do: play with ideas and turn questions in on themselves.
Yep.
So what did Cantor do next? He asked, can I count the things we count with? Can I actually count the set of counting numbers?
Right.
A wonderful idea.
Right, so there they are.
They're
1,
the counting
2, 3,
numbers.
4, and so on and so forth.
And these have this wonderful property. I can pluck out every second number, take out the evens. There they are.
Yep.
I can also pluck out the odds.
Right.
And notice, that set of evens can be put into a one-on-one correspondence with the natural numbers themselves.
Yep, 1 to 2, 2 to 4, 3 to 6.
I'm going to do the
1
same
million
trick.
to 2 million, and
Absolutely.
so on. Right.
So those even numbers have the same cardinality as the natural numbers themselves.
Even though somehow you would think there should be less of them.
Should be half of them.
Right.
But in some sense, no.
Right.
Ditto for the odds.
Right.
So I can split an infinite set into two sets of equal size to the original set themselves. Very bizarre.
But a pretty good trick.
A very good trick. Now, some people might say, well, this is not very surprising. I mean, infinity is infinity, so one can do strange things with infinity.
Right.
Not all surprise.
Right.
But the story becomes interesting. There's lots of surprises in the story. Not every number is a counting number, a whole number like this. There are other types of numbers out there. So one can ask, okay, can we do a similar sort of trick with the fractions?
Okay.
In fact, well, I can create a table of all the fractions. There are some repeats on this table. I won't worry about the repeats. But there is a two-dimensional table of fractions.
Right. And so in some sense, that should be sort of the number of natural numbers squared, the number of counting numbers squared, right?
Absolutely. But to me, that feels intuitively more infinite than a one-dimensional infinity of the counting numbers themselves.
Of course, because it has an infinite number of rows, for example.
Absolutely.
An infinite number of rows of an infinite number of things.
So, is that more infinite?
Well, you would think so.
You would think so. But here's Cantor's brilliance.
Yes.
No. The question is, can I put these rational numbers, these fractions, into a single list, like the counting numbers themselves?
Right.
Is there a first one? Is there a second one? A third one? Now, you might go along this table and say, okay, I'll go along the top row.
Right.
Take the first one on the top row, second one on the top row, third one on the top row,
Right.
and merrily go along.
Right.
Trouble is, I'll never get to the second row.
Right.
They'll never get me through the entire table.
Yep. But there is a way to organize them, in fact.
Think diagonally.
Right.
What Cantor did instead, he said, let's weave a pattern along the diagonals.
Yep.
And if you see that, if we follow that path, then yes, there is a first fraction. There's a second fraction, a third fraction.
Right.
So in some sense, I can set up a correspondence between the fractions and the counting numbers themselves. Just like my 5 cats and 5 dogs, there it is.
Right, and that's all you need, actually, to say that something has the same cardinality as the counting numbers, is to find some way to list them.